Hello everyone. In this lecture we will discuss the electrostatic problems. First problem here is find the electric field at distance z above the midpoint of a straight line segment of length 2l which carries a uniform line charge lambda. So as per our problem, suppose the length vary from minus L to plus L, and here this is a midpoint where we want to find the electric field, and the direction of this is z. Okay, at a distance z from the midpoint. Suppose here we have a small element, also here we have small element, then the electric field component is dE due to this segment, and similarly due to another line segment the electric field component again is dE. And suppose this angle is theta, then the resolved components we have, this is a dE sin theta, and similarly on this side we have another dE sin theta, and along this we have dE cos theta, or we have a twice of this dE cos theta. So here suppose the variable quantity is x here, that is the value of x vary from 0 to L, and this distance from this point to point P is r, and similarly from this to this also this is r. Okay, so here the horizontal component will cancel out, so finally what we get dE equals to twice into 1 over 4 pi epsilon naught, and as per our question we can write lambda dx over r square. Here we have cos theta, and z cap is the direction of the direction of the electric field. Actually here this is a variable quantity, that is dx. Okay, then so here we have angle theta, so in this case we have cos theta is equals to z by r, and r is equals to z square plus x square the square root. So if this is, then it mean again cos theta here is equals to z over z square plus x square the square root. Now substitute the value of cos theta and r in this question, in first question, then we can write that is dE equals to 2 into 1 over 4 pi epsilon naught into lambda dx, r square we can write z square plus x square, and cos theta here is equals to z over z square plus x square the square root. Okay, or we can write what we have this 1 over 4 pi epsilon naught into 2 lambda z over z square plus x square the 3 by 2 and dx. So when we integrate this, we can write dE is equals to 1 over 4 pi epsilon naught 2 lambda z, and here we have z square plus x square the power minus 3 by 2 dx, and here limit is vary from 0 to L. So what we get E is equals to 1 over 4 pi epsilon naught into 2 lambda z. So when we solve this integration, then we get x over z square, and here we have z square plus x square the square root, and limit vary from 0 to L. Or we can write 1 over 4 pi epsilon naught into 2 lambda z into, here we have L over z square plus into z square plus L square the square root. So z is cancelled with this, so we can write 1 over 4 pi epsilon naught into 2 lambda L over z square plus L square the square root. So this is the electric field. Okay, so and the direction of the electric field, it is obvious, it is along z direction. Next we have one special case. If z is greater than L, that is the distance where we want to find the electric field is far away from the length, from the line segment, then we can ignore the L value from this equation. So we can write E equals to 1 over 4 pi epsilon naught into 2 lambda L over, when we ignore this, we can write this is equals to z square. So here this question look like a question of electric field for a single charge. So it shows that when we are at a very far distance, and when we want to measure the electric field at a very large distance from the length, then the length look like a point charge. Okay, then we have a second problem. In second problem, we have two infinite plane carries equal but opposite uniform charge density plus minus sigma. Find the field in each of the three regions: first to the left of both, second between them, and third to the right of both. So here, according to problem, we have two infinite planes carry equal but opposite uniform charges. Okay, so as per question, here we have, suppose this is the first plane and this is a second plane, and here suppose the charge density is sigma for first and minus sigma for second, And here suppose we have, this is a first region, this is a second region, and this is a third region. Okay, so first point here is we will discuss the direction of the electric field. Then here we have one equivalent diagram. Suppose this is a plus sigma, and here we have minus sigma. So first point here is, when we have a positive charge, then the electric field move away from this. That is here we have a E positive, that is electric field to positive charge, and here that is it is away from the positive charge, that is in this direction, like this. This is the case when we have positive charges. Now when for negative charge, electric field it towards the charge, that is this is a E negative, here we have E negative, and also this is E negative. So these are the direction of the electric field. Again we have, this is a first region, this is a second region, and this is a third region. Now here, according to Gauss law, the electric field E dot dA is equals to 1 over epsilon naught times total charge enclosed. So here in case of a plane we have a pillbox, and in case of pillbox the area is equals to 2a. Similarly here we have 1 over epsilon naught, charge is sigma into area, so area is cancelled with this, so we get E is equals to 1 over 2 epsilon naught sigma. So here either we have a positive charge or we have a negative charge density. In both the cases the electric field is equals to sigma over 2 epsilon naught. Okay, now here as per our problem, in the region first, electric field, one is E positive and second is E negative, and both are in the opposite direction. So in the region first, net electric field is equals to 0. Now here this is a first case. Now in second, in region second, here one we have a electric field due to positive charge, and second we have electric field due to negative charge. Both are in the same direction, and so total electric field is equals to sigma over 2 epsilon naught plus sigma over 2 epsilon naught, and this is equals to sigma over epsilon naught. Similarly, in third region, that is to right of the both. Now here in region third, again one we have electric field due to positive charge, second we have electric field due to negative charge, and both are in the opposite direction. So again net electric field is equals to 0. So here in this case we have electric field only in between the planes, and after this the electric field is equals to 0. That is, in between the plane electric field is equals to sigma over epsilon naught, and on the left side of the plane electric field is 0, and on the right of both the planes again electric field is equals to 0. Okay, then we have a third problem. In this problem, we are interested to find the potential inside and outside a spherical shell of radius capital R, which carries a uniform surface charge. Set the reference point at infinity. So, first point is, as per problem, here we have a spherical shell and the radius of the spherical shell is R, and we are interested to find the potential at point P, and the reference point is infinity. Okay, and this distance for this is a small r. Now here, for outside the sphere, R is greater than R. Okay, so in this case, electric field is equals to 1 over 4 pi epsilon naught into Q over R square R cap. So electric field is equals to this, but here we are interested to find the potential. So as per definition, potential is equals to minus, here we have reference point to R, and this is E dot dl. Okay, now substitute the value of E here, so we can write minus 1 over 4 pi epsilon naught Q over R square. Here we can write in place of dl, we can write dr, and limit as per problem we set the limit at infinity to R. Okay, then this is equals to minus 1 over 4 pi epsilon naught, here we have a Q R minus 2 dr infinity to R, or this is equals to minus 1 over 4 pi epsilon naught into Q. When we integrate, we get minus 1 to minus 1 infinity to R, or this is equals to 1 over 4 pi epsilon naught into Q over R. So this is the potential outside the sphere. Okay, this is the potential outside the sphere. Now next point here is for inside the sphere. For inside the sphere, R is less than R. So in this condition, electric field is equals to 0. So electric field is equals to 0. So we split the integral into two components, that is VR equals to minus 1 over 4 pi epsilon naught. First component is from infinity to R, that is the radius of a sphere, and here we have a Q over R square dr, and second is electric field, we have a 0 value, so this is a dr R2 small r. Okay, so here this component is equals to 0. So when we solve this, we get 1 over 4 pi epsilon naught. Here we have a Q over R. Okay. So here if we compare these two equations, then in first case for outside a sphere, potential is equals to 1 over 4 pi epsilon naught into Q over R. Here we have a small r, and in this case we have a capital R, that is the radius of the sphere. So when we observe this equation, we observe that although electric field is equals to 0, but still potential, we have some value of potential, and that potential is constant because R is constant and Q is constant here. Okay. Then we have next problem. Find the energy of a uniformly charged spherical shell of total charge Q and radius R. So again here we have a spherical shell and the radius is capital R and the charge is Q. Okay. So here in this case for surface charges, when we have surface charges, then W, that energy, is equals to 1 over 2 sigma V dA. So here sigma is the surface charge density, V is the scalar potential. So here, as we discussed, this scalar potential is equals to 1 over 4 pi epsilon naught into Q over R, and this is a constant quantity. So when we substitute this value in the above equation, we can write 1 over 2. Here we have 1 over 4 pi epsilon naught into Q over R sigma dA, or we can write 1 over 8 pi epsilon naught into Q over R, and this is a sigma dA. So sigma, as we discussed, this is a surface charge density, so we can write as per our question 1 over 8 pi epsilon naught and Q over R, and this is nothing, this is a Q. So this W finally is equals to 1 over 8 pi epsilon naught into Q square over R. Okay, thank you.